Alright, now we're going to start discussing Sylow theory. And we'll start with the first Sylow theorem. So the textbook presents all three Sylow theorems as one major theorem, which gets kind of complicated to present it that way because it's very technical in terms of its statement and in terms of its proof. So instead I will do the other approach, which is to break it up into its individual components. And so the main idea is that Lagrange's theorem tells you that if H is a subgroup of G, then the order of H divides the order of G, or the number of the index of G and H is a divisor of G. They're both equivalent statements. The question is to find a converse to Lagrange's theorem, which is given any divisor, does there exist a subgroup of G with that order? And in general, the question is no. You can find counterexamples, as I have already mentioned in a previous video. A4 is a group of order 12, but it has no subgroup of order 6. Well, there's a corollary to the first Sylow theorem that says Lagrange's theorem, the converse is mostly true, provided that you replace D with a prime power. So if you take any prime power, there exists a subgroup that any prime power that divides the order of your group, then there exists a subgroup of that size. The reason why that's true, well, we'll eventually prove that every subgroup of order power of a prime, okay, I'll state it carefully. If G is order p to the n, you can prove that G has subgroups order p to the k for any k less than n. That's a theorem we'll prove later, though. So usually the first Sylow theorem is stated in a slightly more restrictive manner, and that's the way which is proven, and that's the way in which we will prove it. So in general, you could say that you have subgroups of prime power order as long as the prime power divides the order of your group. But the more precise statement is going to be about which prime power you have. So here's the precise statement. Let P be a prime. Suppose that your group is divisible by P to the n, where n is a non-negative integer, but the order of your group is not divisible by the next higher power of P. Then there exists a subgroup H of order P to the n. So as I mentioned, later we'll prove that groups of order P to the n have subgroups of order P to the k for any k less than or equal to n. So the main step is to prove this one. And such a group is called a Sylow P subgroup. After this theorem, and so the way to think about this is the subgroup whose size is the highest power of P that could possibly be a subgroup of G. And so the claim is that the highest power of P that could be a subgroup actually does happen. So for instance, if G were 168, that factors as, well, at the very least 8 times 21, which is 2 cubed times 3 times 7. Then the theorem tells you that there's a subgroup of order 8, a subgroup of order 3, and at least one subgroup of order 7. Of course, there can't be a subgroup of order 14, and so on. It does not tell you if there's a subgroup of size 21 or 24, so you have to do more work in those cases. It only tells you about these sizes. and it doesn't tell you if there's a subgroup of order 4. Although you know there's a subgroup of order 2 now because, well, we already know for any prime dividing your group, there's an element of order p. What this version of the theorem also doesn't tell you is how many subgroups there are of these sizes. There can be more than one, and in practice there often is. The third Sylow theorem will actually give you a condition on how many such subgroups there are, p subgroups there are. And in fact, this allows me to start saying other terminology. A p group in general is any group whose order is a power of a prime, and same thing for subgroup. So a p group is anything that's a power of a prime order, and a p subgroup is any subgroup of prime power order. So the distinguishing feature between these two and a Sylow p subgroup is that a Sylow p subgroup is maximum. It's a maximum p subgroup. It's the largest p subgroup you can possibly have. So let's prove the theorem. And we're going to do the proof by induction on the size of the group. And so one of the things we first consider is, suppose that P divides the size of the center of the group. Then, as we've already discussed before, whenever P divides the size of a group, then there's an element of order P. Why would we need that fact? Well, if you take something in the center, then the cyclic subgroup generated by it is actually normal in the whole group. Why? Because everything in the group commutes with everything in the center. So that's what we wanted. And why would we want such a thing? Well, because then we can define G prime to be G mod the cyclic group generated by X. And we notice that G prime has order smaller than G. So by induction, G prime has a Sylow p subgroup. Let's call it H prime. And let's say it has size p to the n minus 1. Why n minus 1? Well, in here we're assuming p to the n divides g. Because you've divided out by an element of order p, the largest prime divisor of g prime should be p to the n minus 1. So now we just need to create a larger group. Well, let's just think about it. The fourth isomorphism theorem tells you that there's a bijection between subgroups of the quotient and subgroups of your original group that contain the group you're quotienting by. That's just one of those facts we like to take advantage of. So we know there exists a subgroup H such that H mod X is equal to H prime. We're not going to claim anything but uniqueness, we just know such a subgroup exists. And of course, it contains the cyclic group generated by X. So when you quotient it out, you get a group of size p to the n minus 1. It also contains this subgroup of order p, so what size does H have? Well, it has to be P to the N. Why? Because it's definitely the size of H mod X times the size of X by Lagrange's theorem. And so that's size P, and that's size P to the N minus 1. So congratulations, we found a Sylow P subgroup in G. So I'm going to leave that conclusion for right now. We were assuming that P divided the order of the center, so the only other case is that it does not. Then we use the class equation. Which means that we've created a bunch of elements for each conjugacy class, chosen distinct representatives, and we know by the class equation that the size of G is equal to the size of the center plus, for each representative of each conjugacy class, the index of the centralizer of that representative in G. Well, P divides the size of G, obviously. P does not divide the center, so we see P can't divide all of these indices. So it can't divide one of the indices, at least one of the indices for one of the centralizers. Could be more than one, but one is going to be all we need to get this proof to work. Well, I mean, what is the index? By definition, it's the size of the group divided by the size of the centralizer. And so remember, G is of the order P to the N times stuff. And we're saying that the equation on the left-hand side does not have a factor of P at all. So what can we conclude? We have to conclude that the size of the centralizer is order P to the N times stuff. Note, as I've noted before, the center always has at least one element. It's never the case that this index is the size of the whole group. In particular, it's never the case that this centralizer is the whole group. And why do I need that? Because I need to point out that this is strictly less than G, so that we can apply induction to the centralizer. So by applying induction hypothesis to the centralizer, which is order P to the N times some Q prime, the centralizer has a P subgroup, Sylow P subgroup. Of the appropriate size. But H is a subgroup of the centralizer, which is a subgroup of G. So now G has a subgroup of the right size. And there we have it. So for any prime divisor, take the largest power such that that prime divides your group, you're guaranteed to have a subgroup of that size.